Okay, so let us continue our discussion on second order dynamics. In the previous lecture, we saw the system which is in front of you and we derived the overall transfer function for the system. And what we saw was that if I draw the dynamical response of the system as y versus t, and if this is the step magnitude of the step input, then we made two observations. The first observation was that you always have a response which would be more sluggish compared to the response of the first order system. So, in this particular diagram, the top one is the first order response, the bottom one would be the second order response, and we saw that in no case did the response show any oscillatory behavior. In this particular setup, what was done was that you have a tank in which you give the input, and the output from the first tank was fed as the input for the second tank, but let us go into more details about the construction. The outlet of the first tank is open to atmosphere. Okay. So, in this diagram, when you see that a stream comes out as Q2, this pipe here is open to atmosphere, open to atmosphere, and then you drain the outlet in the second tank. Okay. So, therefore, if you simply remove the second tank from the system, you will start spilling the liquid, you will start draining the liquid, and nothing will happen to the dynamics of the first tank. Now, we may as well have another arrangement. Look here. Now, the outlet from the first tank is going to the second tank, but it is fed in such a manner that the outlet is no more open to the atmosphere, rather it goes to the such a portion of the tank where you already have the liquid. So, in principle, depending upon H1 and H2, you can have the flow of the liquid either from tank 1 to tank 2, or in case where H2 is greater than H1, we know that the flow would be from tank 2 to tank 1. If such is the construction of the system, what would be the transfer function is something which we would be interested in. So, let us look into two constructions. We have first construction in which the liquid is fed to the first tank, the outlet becomes open to atmosphere, and then you put that liquid in the second tank. Okay. So, in our notations, U, Y1, Y2, or to be more intuitive, let us use the usual notations. So, let us do one thing, let us do this, let us use C, the constant flow rate, H1 and H2, and therefore, in this case H1 liquid level in the first tank would be a function of what? It would be a function of C, definitely, nothing to argue about that. It would also be dependent upon H itself, right, H1, let me write dH1 by dt, the time rate of change of H1. So, time rate of change of H1 will depend upon H1, and it would also depend upon the input, okay. And dH2 by dt would depend upon what? It would be some different function. It would now depend upon H1, because the flow rate from tank 1 would depend upon H1. So, therefore, since q2 is a function of h1, dh2 by dt will become a function of h1 and also a function of h2. The time rate of change will depend upon h2. This is pretty straightforward. Now, I have another arrangement in which I have C, I have H1 and I have an arrangement like this. H2. So, therefore, now dH1 by dt in this case would be a function of C, pretty intuitive. It would be a function of H1, pretty intuitive, but as I said, whether H2 is greater than H1 or H1 is greater than H2 will decide the flow between the two tanks. So, therefore, now it will also be dependent upon H2, which was not the case in the first case, right, and dH2 by dt would be a function of what? H1 and H2 both. H2, pretty intuitive to understand this. So, now I have a set of equations which would be different in this particular case. Okay. Now, because dH1 by dt is not only dependent upon C and H1, it also depends upon H2. So, therefore, I need to come up with, I need to devise a method to write a set of equations which would satisfy these conditions. So, let us write our equations in the deviation variable form. So, I can write the first equation as A1 dy 1 by dt. Now, dy 1 by dt would be a function of u y1 and y2 both. As we saw, the liquid level in the first tank was a function of H1 and H2 both. So, I can write this as A1 dy 1 by dt plus A2 y1 plus A3 y2 is equal to A4 u. The only forcing function in the system is u. Okay. What about the dynamical variable y2? Now, for y2 of the level of liquid in the second tank, H1 is acting as a forcing function, right, because if you change H1, H2 will change. There is no direct input which comes as the input to the second tank. The only input is the output from the first tank. So, therefore, now I can write this as B1 dy 2 by dt plus B2 y2. Now, in this scheme of equations, the forcing function is on or the input function is on the right hand side. So, I should write is equal to B3 times y1 because that is the input function. So, I can write this is equal to B3 times y1, or in other words I would simply change it as minus B3 y1 is equal to 0. So, now I have two equations for obtaining my transfer function, equation 1, equation 2. Let me do one thing, let me try to determine the transfer function. I will put the equations in the standard form. I will write this as A1 upon A2 dy 1 by dt plus y1 plus A3 by A2 y2 is equal to A4 by A2 u, the standard form. Similarly, I will put equation 2 in the standard form, B1 by B2 dy 2 by dt plus y2 minus B3 by B2 y1 is equal to 0. Now, time to take the Laplace transform. So, I can write A1 by A2 S plus 1 y1 bar of S plus A3 by A2 y2 bar of S is equal to A4 by A2 u bar of S. The Laplace transform of the first equation and the Laplace transform of the second equation will become B1 by B2 S plus 1 y2 bar of S minus B3 by B2 y1 bar of S is equal to 0. Let me write this as equation 3 and equation 4. Now, what do I need to solve for? My transfer function will involve two quantities. My transfer function would be the one G1 of S, it would involve y1 bar of S divided by u bar of S, and my overall transfer function G of S would involve y2 bar of S divided by u bar of S. Now, I have two equations and therefore, I can solve for y1 bar of S and y2 bar of S in terms of u bar of S and get my transfer function. Okay. Transfer functions 5 and 6. Let me repeat what I just said. You have this equation of the form, if I write y1 bar of S as x and y2 bar of S as y, and in fact u bar of S as z, then I have equation of the form A x plus b y is equal to c z and d x minus e y is equal to 0. This is the functional form of the two equations given by equation 3 and 4, where A is A1 by A2 S plus 1, B is A3 by A2, C is A4 by A2, D is B1 by B2 S plus 1 and E is B3 by B2. So, you will solve for x, you will solve for y, which means you will solve for y1 of y1 s bar and you will solve for y2 s bar and you will get this transfer function. So, I am writing the final expression here. The final expression that you should get by doing this mathematical jugglery is something which is in front of you, y1 bar of s upon u bar of s. What is this? Which we wrote in the previous slide as G1 of S, the transfer function of only the first dynamics of the first tank. This is equal to what? This is equal to A4B1 S plus B2A4 upon A2B2 plus A3B3 divided by A1 B1 upon A2 B2 plus A3 B3 S squared plus A1 B2 plus A2 B1 upon A2 B2 plus A3 B3 S plus 1, right. So, this is the transfer function giving the dynamics of the first tank. We will analyze this. This is an interesting case, but before that let me write down the overall dynamics of the system. G of S is equal to y 2 bar of S divided by u bar of S, and this is A 4 B 3 divided by A 2 B 2 plus A 3 B 3 divided by A 1 B 1 upon A 2 B 2 plus A 3 B 3 squared plus A 1 B 2 plus A 2 B 1 divided by A 2 B 2 plus A 3 B 3 S plus 1. Okay. Well, the expressions look a little complicated, but actually there is nothing complicated in it, because A 1, A 2, A 3, A 4, B 1, B 2, B 3, they are all constants. So, you all of these expressions which look a little complex will have some numerical values, and those values have to be plugged in, nothing great in that. But what we need to understand is something which is very interesting. Let us look at the overall transfer function. The overall transfer function is of the form which is, if I put A 4 B 3 plus A 2 B 2 plus A 3 B 3, the numerator as some constant C 1. Similarly, I club all those constants. So, I will get C 2 S squared plus C 3 S plus 1, right. So, this is the form of the transfer function. So, what is the order of the dynamics of the system overall? Well, for such a case, I look into the denominator, I look the degree of the polynomial, and I decide upon that. So, therefore, the order of the overall dynamics of the system is 2, and the moment I see 2 here, I know that the dynamics of my system, the overall dynamics of my system is going to be slower compared to the dynamics of single tank if the second tank were not there. Well, whether I use this formulation or the particular format which I used previously, the particular arrangement, I anyway got this. But what I see is something interesting here in the first transfer function. If I plug in all of these, I get d 1 upon, in fact not, d 1 s plus d 2. You see there is an s in the numerator. So, d 1 s plus d 2 divided by d 3 s squared plus d 4 s plus 1. So, first of all, the first question which arises is that what is the order, because well, if I just see the denominator, then I see the degree of the polynomial in the denominator, and then from there itself you can see that the tank 1, which used to be an independent unit in the previous case, and that is why it used, the previous case is referred to as the non-interacting case, used to have the order 1. Here if you just look at the denominator, the order is not 1, it has to be at least 2. but there is something in the numerator as well. So, how would you define the order of a system when you have some polynomial in the numerator and some polynomial in the denominator as well? We will take this particular topic in the next lecture, but before that what we need to look into is into this particular aspect is that now your first tank is no more an independent unit, and that is why it is called an interacting system. So, you cannot expect simply first order dynamics even in the first tank. Forget about the entire dynamics, you do not have simple first order dynamics even in the first tank, and therefore, the arrangement which is given like this is called a non interacting system, because if you remove any of the tanks downstream, the dynamics of the tanks upstream does not change, it is immaterial, they are not interacting in fact. Okay. So, the downstream dynamics does not affect the upstream dynamics, the upstream dynamics will always affect the downstream dynamics. So, that is not the meaning of non interacting. The meaning of non interacting is that the downstream dynamics is not affecting the upstream dynamics. Now, on the other hand, you have a system like this, where the dynamics of the second tank is affecting the dynamics of the first tank, and therefore, this is called an interacting system. Okay. And the transfer function form is very different. We will study the dynamics of such systems a little later. But what you saw in general was that the dynamics of a second and higher order system is sluggish compared to the dynamics of first order system, and it is guaranteed to be sluggish as well as monotonous when you have the case when you simply have the multiplication of individual transfer functions as the overall transfer function. Now, we had a look into this particular aspect of second order dynamics, where you have the spring mass system, and in this spring mass system we saw that in fact you can have a damped behavior and you can have oscillatory behavior. Okay. In fact, what you saw was that the oscillations could die down, the oscillations could the response can be such that not oscillations would die down, the response would be such that there is no oscillation, the oscillations could die down, the oscillations may increase in magnitude amplitude, and finally, they may be sustained in magnitude, right. We saw all four. In the previous case, we saw only monotonous behavior, but then how would you get this all of these responses from a second order system in transform domain? Let's look into that. So, imagine that I can write a general second order system as A2 d2y by dt squared plus A1 dy by dt plus A0 y is equal to v times u, the general second order system, right. For spring mass system also, spring mass system with damping, with external forced oscillations, this is a perfect example, right. So, I will try to determine the transfer function. I will do this in this exact same manner as I did previously. I will make the coefficient of y as unity. So, I can write this as a2 by a0 d2y by dt squared plus a1 by a0 y dy by dt plus y is equal to b by a0 u. I am assuming the equation to be in deviation variable form, and for this particular case, as I had assigned a1 by a0 as time constant tau and b by a as static gain k, in this system I assign a2 by a0 as tau squared, which basically means natural frequency of oscillations in the system. A1 by a0 is 2 zeta tau, where zeta is the damping coefficient and b by a0 as usual is the static gain of the system. So, I can write this as tau squared d2y by dt squared plus 2 tau zeta dy by dt plus y is equal to k times u. Now, the next step would be to determine the to do the Laplace transformation. So, this would be equal to tau squared s squared y bar s plus 2 zeta tau s y bar of s plus y bar of s is equal to k u bar of s, from where I get the second order transfer function y bar of s divided by u bar of s as k upon tau squared s squared plus 2 zeta tau s plus 1, right. So, is it a second order transfer function, or is the order second order corresponding to this transfer function? Well, you can look at the denominator of the transfer function, look at the degree of the polynomial, and this in fact is a second order polynomial. So, therefore, the system corresponding to this transfer function is in fact a second order transfer function. But now, how would I determine the response? Well, it is not very difficult. I will determine the response in the exact same manner as I determine the response for a first order system. So, what I will do is, for example, for a response subjected to a step input, what I will do, I will have y of t, which will be given as Laplace inverse of what? A, the magnitude of the step, times k divided by s tau squared s squared plus 2 zeta tau s plus 1, right. And how would I determine the response? Well, I will need to do partial fractions, right. So, I assume that there is a way that I will be able to split the quadratic polynomial and I would be able to factorize it. So, what will happen? L inverse a k, and this would be s minus a s minus b, assuming that I will be in a position to do this factorization, and this factorization is always possible. Okay. So, I will put this expression in this form, and then I will do further partial fraction, invert it, determine the response. And when I do that, then depending upon a and b, the roots of the polynomial, I will get different behaviors. Okay. So, therefore, when a and b are complex, you will get. So, if this is y, this is t, and this is the enforced input. When A and B are complex and they will be complex conjugates, you will get an oscillator behavior. Do you see an oscillatory behavior for complex eigenvalues in the previous state space domain analysis? Yes, we do see this, right. When you have a system where they are purely imaginary, you will see when they are purely real, then what will happen? In that case, real distinct roots, you will see a monotonous behavior, and then you will see one particular case where when the two roots become equal, and then that is the critically damped response, and that is the fastest response that you can obtain from the system, which is second order. So, in fact, whether you use transform domain analysis or state space domain analysis, you would always see that there is a correspondence between state space domain analysis and transform domain analysis. So, we will stop here today. We looked into one particular case where the transfer function was of the form d1 s plus d2 upon d3 s squared plus d4 s plus 1, right, which means that there was a polynomial in the numerator as well as a polynomial in the denominator, and the very definition of the order of the system became questionable, because you not only have the polynomial in the denominator, following which with the help of the degree of the polynomial you could determine the order, you have a polynomial in the numerator as well. So, is there a new method using which we may need to define the order of the system? We will take this up in the next week. Till then, goodbye.